Each day. 26. E&M part.
All right, and School of Minds is connected, right?
Good morning.
Yeah, good morning.
Let's see the slides.
All right, so we're all here. All right, so don't forget, homework due later today. Are there any questions about the homework?
2C exactly. About
2C,
yeah, program 2C.
which is that the final part of 2?
Yeah, I think to calculate the Hamiltonian.
Oh, to find the Hamiltonian
I
also. I mean, the main part is
Or that from the Hamiltonian we have to get that equation, ordinary equation.
the Schrödinger equation, right? That's right.
I'm getting sort of little
So
bit
it's-
confused.
What?
I'm not getting the idea how to do.
So, okay, so maybe, let me look back also. So, ideally too, the homework was sort of set up based on the lecture, right? So let me back up to what we were doing. I mean, right, one of the things we sort of started out with, right, was we started out with our classical field, right? We applied this ansatz, right? To make it non-relativistic. E to the I minus IMT and this is what we define psi, right? Non-relativistic classical field. And the funny thing was that B obeys Schrödinger equation, or Schrödinger-like, because, right, we just basically were saying this guy applies to, he's normal Klein-Gordon, he satisfies the normal Klein-Gordon equation, which is classical. And we applied that ansatz and took the non-relativistic limit, meaning momenta are small compared to m, and then we found the Schrödinger-like equation, right? For a free theory in particular, we found, it looks like time derivative basically of the psi is equal to a kinetic term, right? So it looks like it looks like the Schrödinger equation for a non-interacting field. But that's just suggested because this thing is still classical, right? We want to have a probability interpretation for him. So that was the idea with, I think, 2b, right, in the homework, where we can construct things like position operators and the position eigenstates, and then we could make up some generalized state, right? This is what I meant by this phi, which, by the way, is not related to this phi, really. I mean, it's not equal to at least, right? Maybe I should have used a different notation, but once we have the idea of what position eigenstates are, I can ask what's the most general state, right? The thing that's an arbitrary superposition of position eigenstates, weighted by this thing, phi. This actually gives me a probability interpretation. It's associated with the likelihood that I find the particle at position x. So I could think of this as my normal sort of Schrödinger wave function. At least it seems like it, right? And the non-trivial part, the main thing you're asked to show is that this guy actually satisfies the same Schrödinger equation, but now endowed with the correct probability interpretation. And now it's quantum mechanical, right? We looked a little bit at how you do that in class, right? How, again, in retrospect, probably lots of parts of the problem could be clearer and walked through more carefully, because, right, we're starting classical. And what's the idea? That I think classically now about what's my Lagrangian, what's my Hamiltonian, and those canonically conjugate momenta, and then I promote those to non-commuting operators, right? And that's how I quantize the theory. So that's the logic. We want to take a classical theory that already looks reminiscent of something like the Schrödinger equation, except it's classical, so it's very weird. Now we want to really quantize things for this non-relativistic field and just show that we get back a Schrödinger equation with a probability interpretation. So, are there any other specific questions about it? Yeah, maybe I should have made some other step to set it up a little bit more. But right, basically with those definitions for the position and momentum operator that are given in the problem, you should be able to show x and p satisfy the normal commutation relation. Right. The Hamiltonian degree written in that way. Right. I mean, maybe. Yeah. So, the relative thing. Certainly the Hamiltonian degree written like this. That we basically sort of actually showed in class, I think, right? So you can get that. Yeah, but it'd be helpful, for example, right, if you could write this in terms of annihilation and creation operators, in terms of A and A daggers. That will be helpful for showing that the Schrödinger equation is obeyed. Right, how do I get this into A, P, and AP daggers? All right. So unless there's any other really specific questions about the homework, I'll start in with what we're going to talk about today. Are there any other questions about the homework? Okay. All right, so let's talk about, right, we were sort of in the middle actually. One thing we wanted to look at, which was that Yukawa connection. So this is for today. So the first thing I want to do is finish connecting the classical Yukawa potential that we found. Right? We did that. So this is basically the first step that we did last time. Classical Yukawa potential. I want to connect to that a psi-psi scattering. Regular the scattering Q of t amplitude. So this was looking at the same theory, but I was just looking at it classically. So if I really have this souped up quantum mechanical Lorentz invariant beast, the thing that has all the bells and whistles, there's got to be some limit, right, take so that I can recover the classical result. And in doing this, so we'll do this, we'll show how we go from our full amplitude to get back the Yukawa potential. That'll strengthen also sort of this interpretation, which I've been saying in words, which is that those virtual particles that's doing the mediation of the scattering, the exchange of a phi particle between the sides, that really is responsible for the force. So we'll see that really explicitly when we do establish this connection. We'll also look at, we'll go back to this other sort of simple theory that we talked about, phi to the fourth theory, which has just one particle. It's the simplest model that has interactions in it, if you have only one particle. And we'll look also at the potential in this case. We'll see it's a bit different. It's not a Yukawa potential. And we'll also just finally talk about something really observable, which are decay rates. And then that means next time we'll talk about cross sections, which are only slightly more complicated than decay rates. We're only going to talk about 2-to-2 cross sections, although the formalism we'll build up this general. Okay, any questions about what we'll talk about? Okay. So, right, remember what it is we found, right? We found classically the last time. Found the profile of the field of the classical scalar field falls off as 1 over 4 pi r times e to the minus m r. So it's really Coulomb-like, except it has this additional cutoff. It's not infinite range like the Coulomb force, but it's cut off by the Compton wavelength of the phi boson that's being exchanged. So right, this is all just classic. So how do we get that? How does Q of t include this information? So ultimately, right, it's got to be encoded in our amplitude. In our psi amplitude. So remember what that was, or actually, maybe now, if you've at least sort of been looking over your notes for the Feynman rules, you don't even have to, if the Feynman rules have really been internalized into you, you don't even need to look up what the amplitude is for this thing anymore, because you could just draw 2 diagrams and write down the result. So I'm just going to write down the result because we had what we were calling basically T-channel diagram and a U-channel diagram. U-channel is just the same, looks the same, we just flip some labels around. We found, and here we'll just find out that this sign actually is very important for making the interpretation for the force. Basically, is it a repulsive or attractive force? We found it's plus IG squared, 1 over plus 2 diagrams. P plus P prime. We had a T channel and a U channel contribution. And these are 4 momenta, right? P minus P prime, or P plus P prime. So we've got to take some non-relativistic limit. So let's go center mass frame. And take the non-relativistic limit. Things like magnitude the momenta is small compared to mass of the psi particles. This is the phi mass. If I write little m, I'll try to remember to put a subscript to make it really clear. But certainly the main thing we mean when we take the non-relativistic limit is that the momenta is small compared to the scattering particles. Particles involved directly in the scattering. So this makes that limit easy. So it means basically what we're saying is the main part of the 4 momenta is the mass, right? Not the momentum. Or sorry, the other, mass is the main part. So our amplitude becomes minus just IA plus G squared, and now these guys become 3 vectors. E plus E prime plus M squared. But we have to do some more work. also have to sort of remember how scattering worked in non-relativistic quantum mechanics, which I think we saw when we were, at least in our quantum mechanics class last semester, we saw how to do scattering through a potential in the Born approximation. So we want to compare scattering in non-relativistic quantum mechanics, which we knew how to do at least with some approximation, the Born approximation. This was in that chapter on time-dependent perturbation theory. So this is actually equivalent to doing it this is sort of related to the Dyson series. But there, we found the scattering through a potential for example, momentum eigenstates. So that was given by this sort of expression. How does a P go into a P prime? What's the probability amplitude scattering through a potential U? In the Born approximation, it's minus I, P3R, UR, So we can use this actually to finally match onto our quantum field theory amplitude, the thing we have over on the right-hand side of the board. But to do the right matching, we also have to use the fact that the momentum eigenstates we were using back in the good old days of Shankar in non-relativistic quantum mechanics, those had different normalizations than the ones we're using, because we care about Lorentz invariance, so we wanted everything to have the proper 4 momenta normalization. Remember we made a big deal about that? Or some deal about it, maybe not a big deal. We talked about it. So to do the to match the amplitudes, basically, onto our QFT amplitudes. We need a factor of 2m and psi. So this is from relativistic normalization. So this is really just to start connecting the good old days and what we're doing now. So now we can match D3R, U of R with this exponential, e to the minus I, from plane wave stuff. The right matching is that this is basically the equivalent of our quantum field theory amplitude with that 1 over 2m squared normalization. And also, to make our life as straightforward as possible, I'm going to make the approximation that at low energies, these two contributions, that T and the U diagrams, are the same. So effectively, I'm going to forget about, say, the U diagram. This would become minus G over 2 m psi squared and 1 over P minus P prime squared plus m squared. So we could also, right, since this combination of things is appearing, just write this as minus lambda squared, where now I define this thing as lambda. Lambda is just G over 2 and psi, which is something dimensional. Remember, in the language of relevant, irrelevant, or marginal interactions, the theory we're working with is a relevant interaction, right? Meaning that the coupling we're interested in has units of mass. So this lambda thing is some dimensionless parameter. So that equation actually lets me read off what the potential is, which will be a familiar expression. So it means that the potential, U of r, is just minus lambda squared, the d3 d over 2 pi cubed, is e to the I p r over p squared plus m squared, which is actually the same expression. This is the same expression we had when we were looking at the classical theory for a phi. So we already know the result, right? So this is the same expression as in classical theory. So we could write down right away what's that potential. It's minus lambda squared over 4 pi r e to the minus mr. So that's the idea. But indeed, it has encoded the same information, right? We do the right matching, worry about those factors from a relativistic normalization so that we can correctly compare with the Born approximation. And we get out the same thing we had before in the classical theory. But notice also this, note the minus sign. So this means it's an attractive force, right? So if we wanted to, by the way, we could redo this whole thing. We could go back to, we also looked at Psi-4 scatter. We know how to compute the amplitude in that case too, right? So we could redo everything, do the same matching, and figure out what's the potential in that case, and it's still with the minus sign. This is a feature of scalars. This sort of interaction is universally attractive. So it doesn't matter if it's a particle or an antiparticle, it'll always be attractive. So the other important upshot of this calculation is, right, really showing that virtual particles are responsible for forces. I mean, yeah, it's a really non-trivial result in a sense. Virtual particles are those weird states, right, that don't satisfy the normal p squared equals m squared relation, which sounds very, very mysterious and quantum mechanical, but ultimately it's them that's responsible for forces, even classical forces. Right, and then one last thing I wanted to mention is the sort of general features of the exchange of particles. We're not going to show, but for your knowledge, so spin zero particles are always, the exchange of them at least, is always attractive. Spin one, the relative sign of the particles determines is it repulsive or attractive. And sort of amusingly, to go back to spin, if you go to spin 2, it's again always attractive. So this is like gravity, actually. Gravity is associated with the exchange of a spin 2 particle called the graviton that we don't understand well, but always attractive also. So electromagnetism is sort of a special case. It could be attractive or repulsive. So this helps us establish and also get, this is maybe one step in connecting with something observable, right? Predict that theories like this lead to classical forces, not ones that are infinitely long range, but ones that extend over some region determined by the mass of the exchange particle. So this is also, for example, why, so the guy that it's named for, Yukawa, so nucleons inside of the nucleus, the protons and the neutrons, those exchange pions, keep it confined into a nucleus. And the reason that the strong force took so long to even discover is because that mass is really, leads to a very small confinement scale. I mean, it leads to the fact that this thing doesn't extend very far. Unlike electromagnetism, it can lead to really huge effects on macroscopic distances. The strength of the strong force, although it's big, lambda is big for the strong force, doesn't extend very far, a spatial extent, because of the mass of the pion cuts it off. Okay, so it's actually a really different kind of theory that also leads to a classical force is Psi-4 theory. So this will actually teach us, although most of the time in the standard model, forces are associated with the exchange of virtual particles, the more general statement is that, which is kind of obvious, I guess, but the interactions in the Lagrangian are responsible for forces, because this is associated with the exchange of nothing. So we'll go back to this theory and also ask, what is U of R here? What's the classical potential look like? So I don't remember how long ago we talked about this theory, but our convention was 4 factorial out front. We'll see why that is actually in just a minute. Look at Wick contractions. So this is a convention, let me say, but no one is forcing you to do that, right? You could also, of course, right, this is just a thing parameterizing the strength of the interaction, this lambda. So, if you don't like 4 factorial there, that's fine. It's just defines the meaning of the coefficient in front, basically. Defines the meaning of lambda. So the Feynman rules associated with this are simple. So they're all the same as before, except for the fact that now we have a new interaction plus one new interaction, which is just that we'll see why this is. So the Feynman diagram for this Psi-4 interaction is I have 2 sides come together, 2 phi's rather come together and give me back 2 phi's, so I can have this be P1, P2, whatever. Doesn't matter. All that I get from this is a minus I lambda. So anyway, why, right? We're not being super careful about the writing of Feynman rules, but we can see why roughly it's going to look like this by doing the Wick contraction stuff, right? This is, remember again that we have these 2 methods, right? We could just use Dyson plus Wick to do the calculation, or we could use Feynman. But let's see how it is that this is basically the one Feynman rule we have to know about. We can look at 5 bias scattering. So another interesting thing is that unlike our phi psi theory that happened at g squared for scattering, this scattering happens just at 1 power of lambda, right? It happens at order lambda. getting 1 power of the interaction Hamiltonian. So I'm doing the Dyson series step. And I have to sandwich it between 2 momentum eigenstates. How does a P1, P2 state turn into a P1 prime, P2 prime state? And the Wick theorem tells me I insert it sandwich around a normal ordered insertion of the Hamiltonian. And only one insertion of the Hamiltonian. Also, these are the final states. So any of these fields, right, can do the annihilation or creation. So you can find that there are 4 factorial possible contractions, which I'm not going to write down because that's a lot. But that's the reason that we do this 1 over 4 factorial convention. It's basically just it makes the Feynman rule this. Right? That's the whole reason for doing that normalization. It makes the Feynman rule maximally easy. So, but this also illustrates an important point about, which we're not going to really say anything about right now, but we'll come back to a general, come back to what are called symmetry factors. They're just basically combinatoric factors for taking into account identical particle stuff. But you do need to have correct. It's one of these somewhat annoying bookkeeping things. But you need to worry about those for certain processes. Seems like they come up more when we're dealing with fermions. So, all right, but with this one interaction, by the way, right? So we have our other Feynman rules about how do we treat internal lines and stuff. But this is the nicest possible Feynman diagram because there's no internal lines. So I can write down what the scattering amplitude is, right? I can write down with my new Feynman rules. Remember, we stripped off the delta function stuff so we can compute the amplitude right away. I draw all possible Feynman diagrams. Right, just as, let me back up a second. So just point out, right, with all those contractions, right, this basically shows me all that I'm going to have from this Wick term is going to be minus I lambda. So this is why you get out that that's the right Feynman rule. And then if I want to do things the Feynman rule method, it's easy to write that I draw all possible diagrams at order lambda, it's only 1. And it has only one thing to write down, minus I lambda. So that's it for the amplitude. Which means, by the way, compared to the other sort of amplitudes we've looked at, what this is saying is that there's equal probability to scatter at all angles, for example, and energies. The equal at all energies thing, maybe we should have anticipated because this was what we call a marginal interaction. Remember the difference? The 3 possibilities were irrelevant, relevant, or marginal. And marginal means equal at all energies. That's really what I meant. The other ones, irrelevant, will not be relevant at low energies, so they grow with energy. Relevant was the opposite. So we should have basically been able to guess that it would have some feature like that. So now the final thing is we can translate that to a potential. So what we would do is, again, doing all the same steps, right? We have to do the right normalization and so on. So we have the 1 over 2m squared in front. But the amplitude now is super easy. We just insert this instead of the 1 over p squared plus m squared stuff. So we would get this is plus m squared over 2 m squared and d3p over 2 pi cubed e to the plus I p dot r. And so that integral is the Fourier transform of a stealth function. So it's just a hard interaction. The profile is 0 everywhere. Right, so this is really different than the other case. Which comes from the fact that it's arising from the exchange of no particles. It's just a hard interaction. You either totally hit, you totally scatter, or you don't scatter. So it's just a repulsive, hard interaction. So, not arising from the exchange of any mediators. So it's kind of a funny case, right? It's very ultra short range interaction. Okay, so anyway, there are all kinds of other processes we could study with in the Phi to the 4th theory, but this shows us an interesting thing, especially after we just saw the connection with the Yukawa force. Right, so that's what I would say that the most general sort of lesson is, right, terms in the Lagrangian are ultimately what lead to potentials. Most of the time they're from the exchange of something, but sometimes they're just hard-coded in the Lagrangian. They just tell you how to take two particles of some given momentum and put them in the two particles again of some other momentum. And that, you could generalize that too, right? We could look at lambda phi to the 5th theory. How do you take two particles and through just a hard scattering turn them into 3? Phi to the 5th theory would have that, right? It would just have the same Wick term, but one more. I'd have 5 factorial possible contractions. But there I would find out this is not an energy and probably also not angle independent contribution, because phi to the 5th theory is an irrelevant interaction. So it's going to be growing with energy. But it, yeah, will still have that same delta function-like behavior.
What
Right.
what
Questions?
interactions actually are phi to the 4th in the
In the
real
real
world?
world?
Yeah.
So there's only one. Well, if you're thinking about at least the fundamental interactions, because so pions have an effective one,
Okay.
but pions are also not a fundamental particle. They're built out of quarks and antiquarks.
Yeah.
But I mean, so the only possibility is the only scalar, because phi to the 4th is a particular thing for scalars. You can't write down phi to the 4th for
Right.
fermions. And right, the only option is for the Higgs.
Okay.
Yeah. And that term in the Higgs potential in the standard model is not probed yet, because you'd have to look for Higgs scattering,
Yeah.
which is a hard thing. So there are people who study that though, at some high luminosity versions of the LHC or other future high energy colliders. But as you might imagine, it's hard
Yeah.
to see it. Yeah. I mean, in the standard model though, we can infer what the correct size of lambda is for the Higgs. Because if the standard model is all that there is, then there are only two parameters in the Lagrangian for the Higgs. It's mass term and lambda.
Okay.
And having the correct, those also determine what the vacuum expectation value is, which sets the mass. We know what that number is, the vacuum expectation value. So essentially by knowing the Higgs mass and that expectation value, you can determine lambda.
Okay.
So in the standard model, it's fixed. We have a prediction for what it should be. But, right, if in the future someone does an experiment that can actually probe Higgs scattering, then we'll actually know what the number is. and hopefully find that it's not the standard model value and that there's some other funny physics going on. But, right, does that make sense? So, yeah, it's fixed in the standard model, but observationally, we don't have data on what it really is. Yeah, but since that's the only scalar in the real world, that's the only place it shows up. Yeah, so marginal interactions are really special. Right? There's only one possible case, right, which is a scalar to the fourth power. Everything else is either relevant or irrelevant. All right, so the last part that I talked about in the outline is talk about decay rates. So let's talk about what is measured. So things like decay rates, and also cross-section. So today we'll talk about decay rates, and then next time we'll talk about cross-sections. And then basically finish chapter 4, I believe. And then we'll go back and study fermions. All right, so there's one very important sort of mathematical subtlety. So just as in non-relativistic quantum mechanics, thing controlling real probabilities, like probability to decay or probability to scatter, those are going to go as amplitude squared. And we found always, right, that all the amplitudes are proportional to a delta function. So, right, all of our rates, all of our amplitudes they go as something like some, yeah, I could do A or I could write it as a S matrix, doesn't matter. All of these are proportional to some delta of, say, final momentum minus initial momentum, something like that, right? And, so I want to say, just like on relativistic quantum mechanics, probabilities are proportional to this thing squared. So we're going to have that things like the decay rate or the cross section, those are going to go like a delta function squared. And in particular, like a 4 delta function squared, right? So in our notation, we do little parentheses to denote the dimensionality of the direct delta function. It's going to be some delta to the 4th quantity squared. Which sounds a little scary, right? So we have to figure out how we actually deal with that. But there's a good clue for how we deal with it from non-relativistic quantum mechanics, because this came up. We actually did look at decay in non-relativistic quantum mechanics too, briefly. There we were only worrying about a delta function in time, basically. Because in non-relativistic quantum mechanics we didn't have 4D anything we were caring about. But there's a good clue, so let's actually go back to our old-fashioned way, almost old-fashioned. Yeah, in a sense, well, this is going to be reminiscent. This will actually use the Dyson series, but this will be reminiscent of how we looked at decay in non-relativistic quantum mechanics. So this is something called Fermi's golden rule. Right, so the question is how to deal with delta squared so the question is how does the interaction Hamiltonian turn an I into a F? decay is in an abstract way. We have some initial particle and it turns into some other particles. So we can use Dyson, for example, to do this. This will look a lot like non-relativistic quantum mechanics. Yeah, sorry, this is really, basically using non-relativistic, using the Dyson series there, or equivalently perturbation theory, what we used to call perturbation theory. So this is what I want to compute. I want to figure out what's the amplitude for some n eigenstate. These are both energy eigenstates. Energy eigenstates of energy E sub n and E sub m. So with the propagator in between those, I should be able to figure out what's that amplitude. So Dyson gives me a way to do that propagator. Let me just compute it to first order. I have only one power on the Hamiltonian to worry about. Got my 0 to t, dt prime, each interaction t prime, that acting on n. And right, let's remember, what does the interaction Hamiltonian look like? Remember our prescription for, we're in the interaction picture. So this guy looks like e to the plus I h naught t, which is in the Schrodinger picture, and e to the minus I h naught t. That's how we interpreted it. So this will start looking like something familiar, I think, from non-relativistic quantum mechanics. So when I insert him there, I know actually what the action of h naught is on these energy eigenstates, right? They just give me back the energy, right? But it's all in the exponential. So all that I'll get then in the exponential is back that energy. Right? I could work out order by order because I know what the exponential means in a series. So then I'll get that the right-hand side becomes minus I n h n, and integral 0 to t dt e to the I omega t prime, where this omega is En minus En. And now the integral is easy, right? Just an exponential. So I'd have minus, and also the I will cancel that I, so I'll have just the minus left over. Minus m h to n, and e to the I omega t minus 1 over omega. The 1 is from the 0 on the limits of integration. So then we can get what's the probability to go from n to m, which is some function of time too. So it'll be the square modulus of that thing, of m u t n. So that's not too bad either. Now I don't have to worry about the minus sign. M h n squared and 1 over omega squared. I'm going to pull that out in front. And I'd have I omega t minus 1 into the minus omega t minus 1. Right? Doing the complex conjugate. So what does that give me? let me actually just focus on that part, this exponential. So this would give me a 1 and a minus e to the I omega t minus the minus, and a plus 1, right? So which is in other words 2 minus. So we know this combination is something more convenient. Combination of e to the ix plus e to the minus ix is a cosine with a 2 thrown in. So putting that in, right, this will be 2 minus 2 cos omega t. So we would get probability to go from n to m as a function of time. That same element. 1 minus cosine omega t over omega squared. So if you were to plot this, that's one way to start thinking about this. Get some intuition about what's going on. Plot this as a function of omega, say. So what it looks like, something mostly centered at omega equals 0. So this has the right, since this normalization, it maxes out at 1/2 t squared, and this is basically 2 over t. So you could see, as you take t going to infinity, it looks more and more like a delta function. So, write down the right normalization too. Let me just write down 1 minus cosine omega t over omega squared. That looks like a pi times t of delta omega as time goes to infinity. Which is helpful because then I can write down the probability in that limit, the transition from the state n to the state m. So I still have the same matrix element following me around. And now pi t delta omega. But really, this t is, time going to infinity. So it naively looks like I'm getting something divergent. But what I should do really is write what's the rate of the transition, or rate of decay. So the better and more well-behaved thing to look at is dt of that probability will just be this thing, going as 1 power of delta function. So pi times delta omega. So the reason we're going to use this, there's actually another way to do the same calculation. So at the end, right, we took this limit of time going to infinity. What if we had done that limit earlier? If we'd have done that earlier in the calculation, so let me show that really quick. If we'd have done that limit earlier, we would have encountered a delta function just at the level of the amplitude, not at the level of the probability. So if we had done the calculation in that order, it would have given us something going as delta squared. Since the order doesn't matter, it gives us a way of interpreting what delta squared is. It's ultimately going to be in the right limit, only going to give us 1 power of delta. But let's see that. So the second method, doing basically the same calculation. Let's suppose instead we wanted the states this end state at t going to minus infinity. He's the one in the infinite past. This other state is the one that he evolves into in the far infinite future. So then, in the Dyson series, what we have is this IM, right? Then we have our infinite time interval here right away, HINT, BT. Which would just be minus I m h int n and 2 pi delta omega. So this would be confusing if we'd have done it this way, right? This way is a little more quick and dirty, not really doing the limit in a very careful way, the limit of taking time to infinity. So then, when we square the amplitude, then we find, right, just do this thing. Do same matrix element, but now we have a 2 pi squared and a delta of omega, that whole thing squared. But ultimately, since these two methods have to be the same, we could equate the two expressions for the probability to arrive at a way to deal with delta squared. So this is only sort of half relevant for us because, so this means that 2 pi squared times delta squared, that's 2 pi times delta omega times e. Or this is really, sometimes people write this as capital T, the shorthand for e going to infinity. So the reason this isn't yet exactly relevant for us, it's only schematically relevant because it tells us how to deal with a one-dimensional delta function that's squared. So you could guess what happens if you consider a four-dimensional one. You have just more powers of 2 pi, and instead of being time here, this will be space-time volume, or equivalently just regular spatial volume times time. So the upshot for us, for D, is so we're going to use the right. Maybe I should also. I mean, you can see basically the interpretation, right? So this is, delta squared is 1 over 2 pi times delta times t, right? So the upshot for us will be that 2 pi I could write, I guess. Delta to the fourth thing squared is going to be 1 over 2 pi to the fourth, and delta to the delta 4-dimensional times volume times time. Right? Just basically guessing what it should be for 4 dimensions, assuming there's no funny business from the fact that we have a weird metric for space-time versus delta functions, but that's encoded in how delta functions work, or how at least our 4D delta function that we've already dealt with. So okay, so this is a lot of preliminary stuff about how to deal with this delta function squared. Right, and notice too, right, that this has the right dimensions, so delta functions are always, they have the units of 1 over the units of the argument. So if the arguments are things like momenta, then this delta function has units of 1 over momentum. And 1 over momentum has the same units as position or time. So now we can apply this to decay rates in our quantum field theory. So we may not even finish this. Okay, but let's look at the decay, or the probability. Probability to decay of one single particle to some set of, I think it's read it as some set of final state particles. So it could be some arbitrary number of them, it doesn't matter. So these guys will have, let me say that he has momentum p sub I, and these have momentum c sub f associated with them. And I have to, of course, have that the sum of all their momentum is equal to his initial momentum. But the probability, just even, I guess by definition, really, right? So it'll be probability amplitude squared of the S matrix that connects I to F, all the possible final states, divided by the inner product of F on F and I on. And also, let's remember too what those inner products are for us. So I on I was just 2 pi cubed 2 times the energy associated with momentum p sub I times a delta function at 0. That's just equal to 2 EPI times the spatial volume. So another way, by the way, of just thinking about the confusion that comes when you square a delta function, it looks divergent just because we're considering infinite time or infinite space. So if we don't consider that, then you're not going to have any divergences. Right, and this thing, this inner product, will just be the product of all the final states of the same thing, the 2 EP of F times V. Just all multiplied together. However many there are for the final states. Okay, but anyway, now we know how to start connecting things because we have an expression for the S matrix in terms of the amplitude. Right, we can use this S matrix was I, 2 pi to the 4th, and the amplitude to go from I to F, whatever it is. So that's the thing that depends on your particular theory, times a delta function that accounts for the total conservation of momentum and energy. So in other words, right, this is total final momentum minus total initial momentum. So now we're going to use that trick, right? Because right in the numerator we insert this and we automatically get that delta function squared. So we'll have to use our trick. We'll have the square matrix element, 2 pi. Oh yeah, should have been more careful when doing this, but the delta function, 4-dimensional delta function, squared. In the denominator, we'll have a 2 pi times v, and then times a big product of all of those, 1 over all of those 2 EPFs from the final state particles. This is all product over all the final states. Right, but now we can use this rule, delta function to squared, is 1 over 2 pi to the 4th, times regular delta function with another Vt. So I have AFI squared, 2 pi to the 4th. Right, this 2 pi to the 8th, and I have 4 in the denominator. Still have one more delta function, P times T. 2 EIV. And cancel some V's. And now, still times that product of final states. All right, so far so good with everything. So the other thing that will simplify things is let's go to the rest frame. You can always do a Lorentz boost to the rest frame of the initial particle, so that the energy for him is just the mass. Right? Do these steps roughly make sense so far? So I'm going to erase so that I can write down the final result. It takes some writing. So the last thing is, we again want to look at P over big T. Remember, big T is just the shorthand for little t, and the limit of the little t goes to infinity. So you really want to look at P over T, which we'll call gamma. It's the rate to decay. And also, we'll integrate over all possible momenta. That's the other thing not taken into account here, right? We're saying, here we're just saying, I'm told, I know what the momenta is for the final states. But in reality, I don't know. I have to integrate over all possible momenta, right? All possible momenta for final states. So I should get this now for P over T, which is gamma. have 1 over 2m. Let me pull that part all out. And I'll sum over all the possible final states with an integral at this part with the square matrix element, square amplitude, times this thing we write as d pi, where d pi is basically all the other junk involved. The 2 pi, it's also just called a phase space integral, taking into account all possible lambda energies, consistent with conservation of moment. So where I have this d3 d3p, 2 pi cubed, that's coming from integrating over all possible momentum. So this is the most general form for the decay rate, right? So this would work for any decay, decaying from 1 to 2 particles, 1 to 3, 1 to 4, whatever. Where the evaluation of the d pi phase space thing, phase space integral, that becomes more and more complicated, right? If you have a huge number of particles in the final state. But this also basically gives us a way to deal not just, 2 elements will basically reappear for cross sections. We'll also encounter delta function squared in cross sections, and we'll again have a similar sort of phase space integral we have to worry about. Yeah, but schematically it'll be very, very similar. All right, any questions? So although we're ending early, I think there's a fair amount of material. So maybe it's good to take a break. And we'll finish chapter 4 next time with a little bit more about cross sections, which is just a slight generalization of what we were doing with decay rates. And right, the other important upshot of this, which I already sort of said in words, but now you can see what the whole point is, right? We have Feynman rules to calculate this thing, right? So now we have a machine for turning Feynman rules or amplitudes directly into observable quantities, decay rates of particles, right? So we can ask, you could ask specific questions. What's the rate for a particle of a certain type to decay to specific final states? Or you can ask a broader question, what's its total lifetime? So sum over all possible final states. And that sort of observable, right, I should say, is also called, in addition to being called the decay rate, it's also sometimes called the width. And that's just because we saw it also in those S-channel plot. Remember when we were talking about S-channel diagrams, where you can have a resonance type effect and see a big spike in cross-section as a function of energy. It's not quite a perfect spike, and partly that's because of this decay rate. So in a sense, for resonance calculations, you're really producing that particle in the S-channel, you're producing it on shell, you're really producing it. So then you have to worry about how quickly it decays, or effectively what's its total lifetime. And just visually on that plot for the resonance feature, the decay rate sets the width of the resonance. So that's also why the decay rates are sometimes called widths. All right, so we could, for example, also start calculating, maybe it's a good homework problem, calculate, because we saw what's the decay for phi to go to 2 psis. We found what A was for phi going to 2 psis. So now you can work out what is actually the decay rate, and how does it depend on both masses. So it'll depend not just the mass of the phi will dominantly set what the decay rate is, but the mass of size will also be encoded in the decay rate you get out. And in particular, right, it'll encode the fact that the phase space, or in other words, space of possible momenta you could decay to, is limited more and more once the mass of 2 psi starts approaching the mass of 1 phi, right? The decay rate starts to get very suppressed as you approach that limit, just because there aren't a whole lot of possible momenta you can go to. So anyway, that sounds like a good homework problem for the future, which is really the simplest possible case, right? 1 to 2 decay. But it'll start to give you a feel for real decay rates. All right. Well, see you guys next week.
You want to look at that? Two-way? Or do you guys have a test now?
12:30. You have done 2C?
Just 2A I've got done.
Oh, you have done 2A.
Have you done 2A?
I have tried 2A. I think I have tried 2A and 2B, not 2C. You want to say?
How'd you do? Okay. Yep. Sorry, I thought you said you didn't know how to do 2A, so I kind of.
I have just tried. It's just the question. 2B. You have a 2B? You have a 2B?
Yeah, the B I need help with, but A I did. Do you need help with A?
This way I did the 2B. I think that.
Oh, okay. So 2B. So you took that,
Yeah.
that.
And I think the exact the program is from my thing here.
Given that and that. Okay.
And
So you
this
said
one,
that, yeah, I did that, and then X times that is.
that's the given one. So I think we have to show this one. So
Yep. So so here's where you added.
momentum.
So what did you do here with the zero state?
This is the this is the phi defined from here, and this is the momentum operator in the inhalation case.
Oh yeah, he says
Say that again?
the same way we have to do like introducing this AP and AP diagram. I think you are right.
So this, sorry, I just don't get how you get. So this psi, how do you go from this to be this? Oh, you do. Oh, yeah, yeah.
Introduce the momentum operator.
Yeah, I think what I missed was that you do this dagger on the zero state to get the X. Okay, yeah. And then from there, then you can act on. So that makes sense. P, AP dagger, and then A. So this is what I wasn't getting. So AP.
Psi. So this is just the conjugate e to the power px ipx. So if the AP is just before, so the conjugate to e to the power minus ipx.
Say that again. So
The p is p, right? The
yeah.
so this portion right here. So this portion for this portion. So psi of AP something like will be e to the power ipx. So if the dragger, then this should be the conjugate.
This is just this part is coming from
Yeah.
this part,
So this.
E to the power minus.
and everything is.
Wait. Okay. So I just gotta think about this bit. So that is equal to the e to the minus ipx. So AP acting on that gives you this.
Yeah.
Oh, okay. How is that? What is that again?
I think we are having something like
Is this just the side dragger X or the
Side
result
drag.
after AP acting on side dragger?
the result of a side dragger acting on the AP.
So this is AP acts on that and
Yeah.
gives you this.
Yeah.
Oh yeah. Okay. Because this is. Well, what does this operator do again? It.
This is just the annihilation operator, right?
Yeah.
And it operates something like being a bra, not the kit. So this is like the conjugate,
Yeah.
and the and we would get okay. I forgot that anyway that if it acts on the annihilation operator with the conjugate of the field, I think it gets the order of the
Okay,
integral
I'll look
of
that up.
X. Yeah.
Do you mind if I take a picture of this?
Oh, yeah.
I'm not gonna copy it.
Oh,
but
oh,
I
oh,
just want to
Okay,
think
so-
about it today because I.
You've done all of the rest, right?
Uncle tadi tak ada kacau-kacau kan?
So then, what's the next page is this? So then you did.
Oh yeah, that's the two. No, I haven't done that.
It's
Yeah,
2A,
let's see.
and then page 6, page 7, page 8. It's 10, it's page 10, page 9.
I'm
Go ahead,
sorry,
miss.
I still don't understand that. Really just-
Yes. The homework are so terrible, the quantum field theory.
What's that?
The homeworks are so terrible. I think that for the quantum field theory.
Yeah.
Anyway, the subject is the hard.
Oh yeah,
Top
it's
one.
hard.
Yeah.
Like what he went over in class today is really hard. It's interesting, but it's
It's interesting. Yeah. If we go line by line, we will get more from this.
yeah.
It's hard to do.
I think
For the 2A, have you done the for 2A?
yeah, I think I did it like you.
It's like this,
I think so. Yeah.
but I don't know how to listen. I just
Sorry, I just want to. Oh, after you take a picture, I want to follow that again. Each node.
I've done this way, the 2A.
Okay, so is this the first page? Yeah. So.
I have introduced from the Lagrangian.
Here. So.
Because I have to, I don't know this way.
I'll show you what I did. It was
But
easier.
anyway, you ended up with the the right expression of Nofus current.
The linear matter, okay.
So right there.
Which is okay, but that doesn't mean
Yeah, record. Oh,
So the book says that if you change a field
yeah.
like by symmetry and then you tiller expand it.
Mhm.
So if you go from psi to if you tiller expand you to the I alpha, you get this. So then this is saying psi goes to psi plus. In the book, it's formatted as delta alpha
Oh, yeah.
psi. So delta alpha psi is I alpha psi. Delta.